I need to tell you a brief story about why we care about enantiomers and diastereomers in the first place. But before I do that, I'll just say I'm not going to spend any time in class on the concept of enantiomeric excess and using plane polarized light to discern between two enantiomers. That's a useful thing to be able to do. Your text has everything in it that I would want you to know, and the concept isn't that hard, so I'm going to leave it to you to follow the study guide and learn how to do that. You shouldn't be that worried about it because it's really hard to write difficult questions about it for exams. I just am worried if we dismiss it entirely, I'm worried you'll find it in the future on the MCAT or the DAT or something like that, and then you'll have your curse you, Dr. Price moment. You have those a lot, I know, but in the future you might have one, and I want you to make sure you've at least been exposed to it, okay? Enantiomeric excess, or EE, and using plane polarized light to distinguish chiral molecules. The punchline is that chiral molecules, two enantiomers, will rotate light in opposite directions, and you can use that to tell which enantiomer you have. Okay, so we won't say any more about that, but what I do think is important for you to spend some time on today is the concept that enantiomers have different enantiomers have identical chemical and physical properties, except for how they interact with polarized light and except for how they interact with other chiral molecules. And then on the other hand, diastereomers have different chemical and physical properties. They are easy to tell apart. And that applies not only for diastereomers where you have two molecules and their stereocenters have different configurations at least one but not all stereocenters, but that's also true for non-covalent complexes that are diastereomers of each other. That probably sounds weird, and as I said it, you're like, what on earth are you even talking about? So let me give you real-world example of non-covalent diastereomeric complexes, and then we'll do some zoomed-in biology. Okay, so you're already accepting the fact that your left and right hands are enantiomers, right? And I think I told you last time that your right hand can easily distinguish between somebody else's right hand and somebody else's left hand. For example, if you shake hands with somebody's right hand, that's a nice "how are you, good to meet you" handshake. If you shake your right hand with their left hand, that's more of a enchanté kind of weird experience. And the reason you can tell the differences between those two is those two situations are diastereomers of each other, right? The right hand shake is a diastereomer of the right hand left hand shake, even though your hands are not permanently attached to each other. That's a diastereomeric situation. Same thing in biology. I'm going to sneeze here, sorry. Dang it, no I'm not. I hate it when that happens. Okay, here are two enantiomers of a small molecule, and they both bind the same protein, but they bind in different orientations. So the purple enantiomer has one stereocenter, its configuration is R. The orange enantiomer has the same stereocenter, but its configuration is S. You can see the difference, right? You'd be able to tell that those are enantiomers. Here to the left is what's called a ribbon diagram of a protein non-covalently bound to these inhibitors. Ribbon diagrams are just a way of representing three-dimensional shapes of proteins. We get these shapes from an experiment called X-ray crystallography. We don't need to talk about that in any detail, but it basically gives you a picture of what the atoms are doing and how they're connected in a protein. Because there's so many atoms in a protein, we don't bother to draw them all. We use what's called a ribbon diagram, where we represent some parts of the protein, like the backbone of the protein, as a cartoon. So for example, this spiral over here, that You'll learn later on that is a cartoon of an alpha helix, or a particular arrangement of the protein where the backbone is spiraling up on itself. Then we also show some of the atoms to give some idea of what they're doing in the protein. In this ribbon diagram, all of the carbon atoms in the protein are gray, and the connections between those atoms are shown as sticks. All of the nitrogen atoms are blue, all of the oxygen atoms are red. Let's see, there's a bromine atom that's kind of gold. The atoms in these small molecules are orange. The carbon atoms in the small molecules are orange for the S enantiomer and purple for the R enantiomer. Now this is actually an overlay. If you feel like you're seeing double, that's because you are. This is an overlay of two different crystal structures. The first is the protein with the orange enantiomer, and the second is the crystal structure of the protein with the purple enantiomer. And then we've laid them on top of each other so that you can compare the differences. And you can see that overall, there are some changes in the protein when you bind one enantiomer versus the other. But the biggest change I want you to pay attention to is the fact that the two enantiomers bind to the protein differently. Before I say any more about that, some of you are wondering, what's the deal with the little red spheres? Those are oxygen atoms from water molecules. X-ray crystallography doesn't actually detect hydrogens very well, at least not for proteins. And so each of these is the location where a water molecule is hanging out in the active site of this protein. You can ignore them. It's not important for our story at all today. What I do want you to focus on is the fact that these two enantiomers bind the same protein differently, okay? The portion up here is this six-membered ring with the nitrogen in it. And you can see that that portion overlays for both of the enantiomers. That portion binds in the same spot. But you can see that the rest of the molecule for the purple enantiomer juts out to the right. That's the stereocenter. But because the orange enantiomer has opposite configuration, the rest of the orange enantiomer, oh, I didn't want that to move. Wow, what's going on? The rest of the orange enantiomer juts out to the left. So you can see they bind in different orientations to the same protein. That's, one of these is the right hand shake, the other is the right hand left hand shake. What I'm telling you is because the protein is chiral, the complex of the protein with the purple enantiomer is a diastereomer of the complex of the protein with the orange enantiomer. And those two different complexes, being diastereomers, are different. They have different properties, and they can have different outcomes. Does that make sense? Questions about that? Yeah.
Would that not be the case with an enantiomer? You said that the diastereomer have different properties.
Right. The two enantiomers, if they're not in a chiral environment, they have identical physical properties. But if you put them in a chiral environment, suddenly the two enantiomers are diastereomers of each other.
Okay.
Yeah. Go ahead. Yes, so one of the different properties that diastereomers can have is different rates of reaction. Yep. Okay, so why are we saying this? You should have the expectation that two enantiomers of a chiral molecule can have distinct biological effects because biology is chiral. Now, why do we care about this? Some of you aspire to be physicians and prescribe or dentists, and you'll be prescribing drugs, at least in some cases, for patients to take, medications, right? Some of these medications are chiral. Some of them have stereocenters, and you need to be aware of the potential consequences of of two different enantiomers and their potential different biological outcomes, okay? So, story number one that I think is covered in your text, so we don't need to say a lot about this. There was an anti-emetic drug developed, I think, in the 60s called thalidomide. The one enantiomer of thalidomide was antiemetic. The other enantiomer was a teratogen, meaning it caused mutations and developmental problems in the growing fetus. So this was a major problem, and giving a medication that had both enantiomers in it had disastrous consequences. In fact, with thalidomide, even giving the pure correct enantiomer would also have disastrous consequences because biology, your body would metabolize that pure enantiomer into a mixture of both enantiomers. This can happen. I'll give you some examples of that. So anyway, chirality is really important for the outcome of medications. Now, the FDA knows about this, so the FDA is not interested in approving drugs to be sold as a mixture of two enantiomers when one of the enantiomers has a toxic effect. Okay, so part of drug development, you have to demonstrate that your drug is not toxic. But for what I'm about to say to make sense, you need to understand that it is often easier to make a one-to-one mixture of enantiomers than it is to make the pure enantiomer. We have a term for a one-to-one mixture of enantiomers. We call that a racemate. So that's the term. Or a racemic mixture. A racemate is the 50-50 mixture of enantiomers. And it is easier to make a racemate than it is to make a pure enantiomer. It's easier and cheaper. So, in a drug development program, if you're able to establish early on that the racemate doesn't have any negative toxic effects, then often you just use the racemate as the drug. Even though you might expect one of the two enantiomers to be better than the other, maybe one of the enantiomers has the desired effect, the other one is inactive. But if the one-to-one mixture doesn't have any toxic effects, and if the side effects are tolerable, then it is often cheaper and easier to just market the one-to-one mixture of enantiomers. This is true for ibuprofen. So if you've taken ibuprofen, the R enantiomer for ibuprofen is, let's see, 160 times, no, it's the S enantiomer for ibuprofen, is 160 times more active as a painkiller and an anti-inflammatory than the R enantiomer. But the R enantiomer doesn't have any toxic side effects, and so it's cheaper and easier just to give you the one-to-one mixture. Go ahead.
So how do they predict how strong the dose is going to be if they have a mixture of S?
How do they predict how strong the dose is going to be? You actually do experiments in animals and then ultimately in people to figure out what the dose is, what the dose should be. It's not as evil as that sounds. Actually, you do animal experiments at first. You monitor the blood. There's multiple phases of clinical trials, and the early phases are not even for effectiveness, they're for safety and toxicity. And so if a drug is toxic, it doesn't often make it out of animals. Yep. Okay. So, and sometimes, I mentioned this, but sometimes biology can interconvert enantiomers. And in that case, it's senseless to give somebody just the pure enantiomer because your body's going to end up making both anyway. Ibuprofen is an example of that. Thalidomide is an example of that. For ibuprofen, this proton here at the stereocenter is adjacent to a carbonyl and also adjacent to a benzene ring. And just do a thought experiment in your mind. Imagine if a base removed that proton, the resulting negative charge would be stabilized by resonance, right? And so that proton is more acidic than you would expect for a CH bond, and biology can actually remove that proton. And once you remove that proton, you get to an intermediate. I'll just give you an example of what the conjugate, if you remove that proton, what it would look like. Having removed that proton to generate this resonance stabilized intermediate, you just lost the stereo center there. That's now planar sp2 hybridized. It can be reprotonated from either side. You're going to get both enantiomers when you reprotonate it. So in a case like that, it's pointless to give someone just the one pure enantiomer because your body's going to turn it into both anyway. For ibuprofen, no big deal because the S enantiomer is 100 times more effective than the R enantiomer. The R1 isn't that bad for you. It's perhaps dead weight, but it's cheaper and easier and makes more sense to do that. Also, some of you have asked me in the past in chapter 4 when you learned about sec-butyl and isobutyl and tert-butyl, why do you need to know that? And the answer was, you don't, as long as you can sort of follow along when I say tert-butyl. But this IBU in ibuprofen comes from, dun, 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 the isobutyl group. Okay. I mean, now you know it, it's useless to know, but you know it. Okay, the other reason you want to know about the enantiomer story is because drug companies use it to extend the patent lifetime of their drugs. So you may not know this about drug development, but it's insanely expensive. And you have 14 to 17 years, I'm not sure what it is, from the time you file a patent on a drug to have exclusive rights to marketing and sale of that drug. At the time that your patent expires, then other people can make and market the drug as well. The FDA, this is a policy in the United States to allow drugs to get cheaper over time and to get access to more people. Which is great for consumers. If you are taking a generic medication, you're taking a medication that somebody else invented and then some other company is now making for you because the patent has expired. So a company has a limited number of years to make exclusive money off of their invention. And at the end of that, they go off what's called the patent cliff, where suddenly their revenue drops because the stuff that they were making exclusively, other people can now make and compete with them. All right, so that's background portion number 1. Background portion number 2 is what I already told you, that it's cheaper and easier to make a racemate than to make a pure enantiomer. So, behold, citalopram, which is a selective serotonin reuptake inhibitor. It was invented in the 70s by a company in Denmark. It was, there was many, many years of clinical trials and drug development. It's prescribed for depression. A trade name for citalopram is Celexa. And it was approved in 1998 by the FDA. Okay? I graduated high school. I was a student here in 1998. You guys were not born yet, so this is within my lifetime, but not yours. The patent, because drug development took so long, the patent expired in 2003. So that meant that in the United States, at least, this company had maybe 5 years to make money off of this drug. And the drug development is expensive, so you need to recoup costs so that you can invent even more drugs, and so that's just part of the story. In any case, they had demonstrated, and it would never have been approved if one of the enantiomers had been toxic, but they had demonstrated that the racemate was fine, even though it was the S enantiomer that had the desired biological effects as a selective serotonin reuptake inhibitor. Okay, so the patent was expiring in 2003. They knew about that and they prepared for it because at the same time that the drug was being approved in the United States, the drug company developed in 1997 an enantioselective synthesis of the S enantiomer. And the FDA allows you to get a new patent on the process that creates the S enantiomer only. Okay? So they filed a new drug application in 2001, and FDA approval was in 2002. Now that's not by chance because they knew that their patent cliff was happening in 2003. So they lined things up so that their new S enantiomer approval by the FDA would happen at just as their other patent was expiring. And then they got, again, an additional 10 years on the S enantiomer, okay? Now, they would have to argue if the S enantiomer, well, let's see. Here was the argument that they used. They said the S enantiomer alone has modestly superior effects relative to the racemate in terms of efficacy and tolerability. So it was maybe a little bit better at doing what it was supposed to do, and it maybe had a little bit fewer side effects. And okay, there's that. But look at the difference in price. So in 2009, these are numbers from the UK, 28 tablets of 28 20 milligram tablets of the racemate cost a pound and a quarter. A pound, well, I don't know. Brits don't have quarters, so it's a shilling or something, whatever. So 1.26 pounds, all right? Now look at the price the same year for 28 10 milligram tablets of escitalopram, almost 15 pounds. So that's more than 10 times as expensive. By the way, why is the dose on the S enantiomer lower than the dose on the racemate? Well, it's not necessarily because it's more effective. It's that the racemate has 10 milligrams of dead weight in it. How much S-citalopram is in the racemate? 20 milligrams of it. 10, right? So beware that argument. Some slick sales rep is going to tell you 10 milligrams of S-citalopram are more effective than 20 milligrams of, or they'll tell you, no, this is the way the argument would go. 10 milligrams of escitalopram is just as effective as 20 milligrams of citalopram. And you're like, oh, less drug for the same effect. Correct or incorrect? False. Throw that guy out of your office. He's lying to you because there's only 10 milligrams of escitalopram in the racemate. Does that make sense? Yeah. Did the company that originally had the patent stop making the racemate? I don't know. Probably because everybody else was making it and selling it as a generic. Yeah. Other questions? Did I miss somebody? Yeah.
If sigma bonds can just rotate freely, how do they isolate just one?
So if sigma bonds can rotate freely, how do they isolate just one enantiomer? Remember, enantiomers can't be converted by rotation around sigma bonds. Yep. But your question is chemically, how would you make one pure enantiomer versus the other? Great question. You must either start with a chiral starting material, and then you can convert, and I will show you reactions where you can get a desired stereochemical outcome. We'll do that very soon. The other thing that you can do that we won't talk about as much in this class is there are reactions where if you use a chiral catalyst, you can favor one enantiomer versus the other. So it's harder, but we have tools to do it. It's just more expensive. Yeah?
How do these companies go about synthesizing completely new compounds?
How do they go about synthesizing completely new compounds? They hire PhD organic chemists who work in the lab to invent them.
Do you just dump them in a liquid and do the thing?
Do you just throw stuff in the liquid? No, I will teach you how to do reactions and synthesis, and you'll get an idea of how you can use known reactions to invent new molecules. But yeah, we're going there. Others? Okay, so maybe there's a legitimate argument there, right? Because the 10 milligrams of the wrong enantiomer might have been having some undesired side effect that the S enantiomer doesn't have. That's a perfectly valid argument. But what you as the physician have to decide is that modest benefit worth the more than 10 times cost to the patient and to the healthcare system? It's certainly worth it to the drug company who gets an additional 10 years of patent lifetime. But they have to convince you, the physician, that the pure enantiomer is better. And so this is complicated, and you'll need to be thinking about it. There's a lot of stories in drug development that are like this. The strategy is called patent evergreening. You just want to be aware of it, and you want to make sure that you're not falling for stupid arguments The argument that the S-citalopram has fewer side effects than the racemate, that's a decent argument if the difference in side effects is strong enough. The argument that 10 milligrams of S-citalopram does the same thing as 20 milligrams of the racemate is a stupid argument which you should not believe because of the reasons we've talked about. All right. So with that, we need to move on to chapter 6, which is going to be about how reactions happen and why. We're going to deal with why first and then how second. So the issue of why reactions happen is essentially an issue of thermodynamics. And when we say thermodynamics, you need to be thinking about your Gen Chem experience and this delta G equals delta H minus T delta S, right? So delta G is free energy. Processes that are favorable have free energy changes that are negative. Or in other words, we will call it downhill. So we want to develop some sort of predictive tools to be able to have a sense for whether a reaction is going to be downhill or not. There are two components to free energy. We talked about them before. One of them is entropy or disorder. In general, we're going to assume that for the most part in organic reactions, we're going to assume that the change in entropy is close to zero. That's going to be a decent assumption most of the time, except for what I'm going to tell you now. Now, anytime I say exceptions, somebody out there wants to know, okay, fine, how do I calculate how impactful those exceptions are? We're not going to do that. I'm not going to provide any tools for that. You just mostly want to have a qualitative sense for when entropy might be something you should worry about. In general, you can assume that it's going to be close to zero unless or except in the following cases. When you make a ring in an organic reaction, that's called a cyclization reaction. That often reduces disorder because, as you've seen, if you played around with a model set, you can move a 6-carbon chain, a linear chain, around in a lot more ways than you can move a cyclohexane ring. Being in a ring reduces entropy. Another case that you want to be aware of is when you take two starting materials. Starting materials means reactants, and you get one product, meaning you turn two things into one. That can lead to a decrease in entropy. Making a ring can lead to a decrease in entropy. In contrast, when you take one starting material and get two or more products, when you convert one thing into two, that can increase disorder because those two or three things can move relative to each other. And then finally, when one of the products of a reaction is a gas, that leads to a massive increase in entropy because gases are way more disordered than liquids are. So those are just, again, qualitative rules of thumb you want to be aware of. It's, I'm never going to put you in a situation where it's like, is this reaction favorable? And you're like, I think it would be, except for it's a situation where I need to worry about entropy. I'm not going to try to trick you about that, but you should be aware of situations where you want to pay attention to entropy. We'll mention reactions in the future, and I'm going to say to you, this is really, really favorable and irreversible, and it's because one of the products is a gas, and I need you to not be like, huh? Why is that? I need you to be like, oh, it's because entropy increased so much, okay? All right, second, enthalpy. In organic chemistry, what we're going to be considering with enthalpy is essentially the strength of the bonds that we form versus the bonds that are broken in a process. Breaking bonds is always unfavorable and making bonds is always favorable. Whether it's overall favorable depends on whether the bonds you form are stronger than the bonds you broke. And in this, we need to correct a misunderstanding that you may have picked up from earlier classes. How many of you have ever heard somebody tell you, oh yeah, ATP is a really reactive molecule, and when you break the bond in ATP, it releases energy? Yeah, somebody's told you that? That is false. It is true from a certain point of view, but it's not even like Obi-Wan true, okay? So, oh, come on, you guys know what I'm talking about. You don't? Okay. Teach us the ways of the Force. Yeah, so spoiler alert, Anakin Skywalker is Darth Vader. Yeah. And spoiler alert, Darth Vader, Anakin Skywalker is Luke Skywalker's father. Obi-Wan tells Luke that Darth Vader betrayed and murdered his father. And then Luke later learns, because actually George Lucas decides in the meantime that Darth Vader was his father. Luke learns that he's his actual father. He confronts Obi-Wan. Obi-Wan says, what I told you was true from a certain point of view. When Anakin became Darth Vader, the good man that was your father ceased to be. Anyway, so there's a bunch of Star Wars lore in there, but the Obi-Wan reference is what I told you was what you were told was true, but only from a certain point of view. And here is the point. Breaking bonds is always unfavorable. But if you replace them with stronger bonds, then overall the process becomes favorable. So I'll show you how that works with ATP in a little bit. But I need you to know that breaking bonds is always unfavorable. Making bonds is always favorable. By the way, I can go toe-to-toe with anyone on Star Wars lore. I don't know the expanded universe that well, though back in 1998 when that company was developing citalopram, I had already read a ton of expanded universe books. In any case, though, if you want to come debate with me about the Clone Wars animated series or anything, happy to do that. I can go toe-to-toe with you. Let's talk about how to know whether the bonds you break are stronger than the bonds that you formed. So I'm going to introduce something called bond dissociation enthalpy. This is there's going to be a tabulated list of values in tables in your text. I'll give you some on the pKa table for the exam, but these are ways you can tell how strong a bond is. A bond dissociation enthalpy is the change in enthalpy for a reaction where all you do is you break a bond. So for example, if we convert hydrogen, H2, into two separated hydrogen atoms, and this happens, you apply a bunch of energy, you break the bond between the two atoms, then you end up with two hydrogen atoms. The change in enthalpy for that reaction is called the bond dissociation enthalpy. That's the energy you have to put in to cause the bond to dissociate. And that is about 105 kilocalories per mole. Some of you may prefer kilojoules, that's fine. There's about 4 kilojoules per kilocalorie. So we'll let you do the conversion there. So if you have a reaction and you can identify the bonds that you break versus the bonds that you form, you can estimate the enthalpy change for the reaction. Let me give you an example. Here is a substitution reaction where we take this alkyl chloride molecule that has a carbon-chlorine bond, and then water, and we're going to ask what basically is the equilibrium constant, or is this reaction uphill or downhill? The product has an OH in place of the chloride and then has HCl. Now notice overall that the change in the number of starting materials versus products is, we don't change the number of starting materials versus products. We start with 2 molecules, we end with 2 molecules. So we're going to assume overall that, and the assumption that the change in entropy for the reaction is close to 0 should be good. If that's true, then we can approximate whether the reaction is overall favorable by looking at only enthalpy, which is going to be bonds formed versus bonds broken. So let's first figure out which bonds we break in this process. Which bonds in the starting material aren't there in the product? Yep, the carbon, chlorine, good, and one more. Yep, hydrogen, oxygen. There you go. So we break the carbon, chlorine, sigma bond. We also break an oxygen, hydrogen, sigma bond. How about bonds that we make, which are made here? Yep, carbon, oxygen, sigma, and then also a hydrogen chloride sigma bond. Okay. So we can look up the bond dissociation enthalpies for the bonds that we broke. If we do that, we would see, and I only have these numbers in kilojoules, so I didn't convert them to kcals, but that's fine. The carbon-chlorine bond, if we break it, that's uphill in energy by 331 kilojoules per mole. The OH bond, if we break that, that's uphill by 498 kilojoules per mole. Incidentally, this tells you that an OH bond is stronger than a CCl bond because it takes more energy to break the OH bond. That's a factor of the fact that H hydrogen is small, so the bond is short and stable, whereas chlorine is larger, so the carbon-chlorine bond is longer and weaker. Now, if we look at a carbon-oxygen bond, we need to figure out how much energy is released when we make a carbon-oxygen bond. The bond dissociation enthalpy for carbon-oxygen is 401 kilojoules per mole. But should this number be positive or negative? It's got to be negative because you're making a bond. So you're going to look up the number in the table. The number in the table tells you how much energy it takes to break a carbon-oxygen bond. You got to be smart enough to turn it negative because you know you're making a bond. Okay? Then for the HCl, making an HCl bond would be downhill by about 431 kilojoules per mole. So you add all of that up together. Bond dissociation enthalpies for bonds broken are positive. Then you've got to turn them negative for the bonds that you form. Overall, that's downhill by about 3 kilojoules per mole. So we're estimating that delta G and delta H and delta G are about minus 3 kilojoules per mole. And if you wanted to turn that into kilocalories, that would be around minus 0.7 kilocalories per mole. So that would tell us that this reaction is downhill, that the products are more stable than the starting materials, and that is why the reaction happens. Go ahead.
This question might be a little bit out there, but it's about the entropy and like bond form. So if it's more stable, like it's favorable to form bonds, and it's unfavorable to break bonds, then why is entropy also like those still contradictory? Like we want to form bonds, but we want more disorder.
Right, so it's the question is if bond forming is always energetically favorable and bond breaking is always energetically unfavorable in terms of enthalpy, then how does entropy, I thought entropy had to increase, and wouldn't breaking bonds increase entropy? Yes, but it's complicated. And in general, this is why I said, in general, the entropy change in a reaction tends to be low. And so the thing that dominates is just the strength of the bonds. In this case, we broke 2 bonds, but we also made 2 new bonds. So in terms of entropy, it's about a wash. But in terms of enthalpy, the bonds we made were more stable than the bonds we broke. And that'll be the major driving force. Now you'll come up with situations where entropy will be really strong for a process, and that'll drive something forward, and I'll point those out as we get to them. Yeah.
There ever be a time where the chart is going to give us what the kilojoule per mole or kilocal per mole is for forming of a benzene ring or something like that?
Let's see, could you get, would there be something on the chart for forming a benzene ring? Those numbers exist. I'm trying to think of, I'm trying to think of a context where I would use that, but yeah, it is known, and you can get a sense for it. And we maybe will refer back to that at some point, but not now. Yeah, go ahead.
So if you summed up the energy it took to break the bonds, is that equal to the activation energy?
If you sum up the energy it took to break the bonds without making them, would that give you an estimate of activation energy? It might not be exactly right, but it would be close. And I'll maybe show you that in just a little bit. Yeah.
In this class, will I typically do that? Or just always assume that entropy is zero? Or will it
Yeah, you will mostly assume that the entropy change is zero. I told you places where you would be worried about entropy, and that's you're starting to want to know, how do I adjust my calculation, and you're overthinking it. You just want to be you just want to anticipate times where you might say, oh, this is what I expect from enthalpy, but maybe it's a little bit different because of entropy, and that's good enough. Okay, yes?
Would you have to have like a catalyst to produce this type of reaction?
Would you have to have a catalyst? Some reactions go faster with catalysts, but we're not talking, catalysts don't change thermodynamics at all. They just change the rate of the reaction. And so this is a question of why the reaction happens, and reactions happen because the product is more stable than the starting material. We'll get to the issue of how reactions happen and catalysts. Before we do that, I just want to point out one thing. I don't want to take the time to draw it because the structures themselves are not particularly important. But I want to just demonstrate the ATP case. Here is a reaction from metabolism in which glucose becomes glucose 6-phosphate. We break an OH bond here, and we replace it with an oxygen phosphorus bond here. This is ATP. This is the bond that we break in this reaction. It's a bond between oxygen and phosphorus. And here is a new oxygen-hydrogen bond that we make. This is the free energy change of this reaction. It's downhill by almost 18 kilojoules per mole. And it's downhill not because the bond that you broke released energy, but because the bond that you made is stronger than the bonds that you broke. Here we're replacing one OH bond with a similar OH bond, probably not a huge difference there. It's not clear to you right now. By the time you take 352, we'll talk about it and it will be obvious. But this bond here is much weaker than this oxygen phosphorus bond here. So the point is this reaction is favorable not because when you break apart ATP, suddenly magic power is released. It's because the bonds that you make are more stable than the bonds that you broke. Yeah?
So when you go from weaker bonds to stronger bonds, you're going downhill,
Yep.
meaning it's more favorable?
Yep, weaker bonds to stronger bonds is downhill in energy, more favorable. Okay, all right. Now we need to start talking about why, let's see, kinetics, kinetics is an issue of how reactions happen. And you might ask, in what order are bonds broken versus formed? And you might also ask, how fast? Kinetics gives you insight into the mechanism of a reaction, and often mechanism is key to being able to predict outcomes of reactions, so that you don't just have to memorize a bunch of reactions and a bunch of numbers in tables. If you understand mechanism, you can predict outcome. You can also generate hypotheses for improving reactions. So let me illustrate the issue of kinetics with an example. Here is a substitution reaction. Cn minus is going to be our nucleophile. CH3I, or methyl iodide, is going to be our electrophile. And then we're going to have two products. One is the substitution product, in which the Cn minus nucleophile is now attached to the carbon. And the other is going to be the leaving group product, in which I minus is just on its own. We'll We'll introduce this term maybe another time, but we'll call this the leaving group. And this is the substitution product. This is a classic example of a substitution reaction. You swap out cyanide for iodide. And if you were to do the math, you look at this reaction, we're breaking a Ci bond. We're also making a new carbon-carbon bond. And the carbon-carbon bond we make is more favorable, more strong than the carbon-iodide bond we broke. So we expect this reaction to be downhill. There's actually more considerations than that. For a full consideration, you would need to compare the stability of the negatively charged I- with the stability of the negatively charged Cn-. We'll talk about that another time. But for now, just accept that this reaction would be downhill. Now, that's an issue of thermodynamics, but we want to know in what order do we make and break the bonds. In other words, do we make the C-Cn bond first and then break the Ci bond? Do we break the Ci bond first and then make the C-Cn bond? Or do both things happen sort of at the same time? And those are questions that are important because they have consequences in terms of the outcome of the reaction, and they can help us to design better reactions. So let's just come up with a mechanistic hypothesis and then make some predictions about what we would see if the reaction did indeed follow this mechanism. So hypothesis number one would be, let's do this reaction stepwise such that, and please do not misunderstand me, I am not endorsing this hypothesis. I'm merely stating what it is and then saying what the predictions are. Let's propose stepwise we break the carbon iodide sigma first, we get some kind of intermediate, and then we make the C-Cn bond last, okay? So if we were to propose this mechanism and draw it out, what would this look like? Well, we'd start with carbon methyl iodide. Iodine would leave, so this would be our starting material. Iodine would leave, and we would get an intermediate that had a positively charged carbon and a negatively charged iodide. Those would be separate from each other, and this would be an intermediate. Now you tell me, based on what you understand about bond breaking versus bond forming, is this uphill or downhill in energy? Very uphill. Breaking a bond is uphill, and you haven't even compensated for it by making a bond. So you expect the intermediates to be higher in energy than the starting materials. Along the way, you predict that you would go through an energy maximum called a transition state. We'll indicate a transition state with brackets and a double dagger to indicate that this is a high energy maximum. We'll put a delta plus on the carbon, a delta minus on the iodide to indicate that this bond is in the process of breaking, and that, but it's not entirely broken yet. It might be difficult for you to understand why this transition state, if the bond isn't completely broken, might be higher in energy than this intermediate. That's complicated enough that we don't necessarily need to talk about it. I will say that there's probably some electron repulsion between CH bonds that hasn't been compensated for by the new Ci bond. In any case, we are out of time. I'm still talking and the class is over. So we'll stop now. We'll pick up that on Monday. I will see you then. Have a good weekend.